few seconds now, both as a researcher, scientist, and as manager, director of centers worldwide, from US to Europe to Japan. In his career, it has obtained a lot of important research achievements, in particular in the field of speech processing, robust speech recognition, and received awards at international level, very important also recently. Ooh, it's yours. And he is also director of the Center for Language and Speech Processing at Johns Hopkins University, that is who gave us the possibility of this event. So thanks also for this. Thanks to be here today, and welcome to the stage.
So since I realized that you are giving up the time for preparing the slides, and also when I heard Mauricio to tell how much I already have done in speech, I decided to do something more useful. Namely, I'd like to tell you about a technique, how you can make energy for free. And the process is following. So you have a box which is filled with the slow molecules and fast molecules. And then you have a little guy here, Maxwell Demon, after Professor Maxwell from the 19th century of Maxwell equations, who, whenever the fast molecule comes, it opens the door, and whenever the slow molecule comes, closes the door. So after a while, you know what happens is that you will have the box. On one side, there are fast molecules. On the other side, there are slow molecules. And you have a temperature gradient. And of course, you can make the energy. However, you have to start thinking that there is a problem, because the demon is a demon, of course. Demon must know which of the molecules are fast and which ones are slow. So you need the knowledge. And for this, basically, if you want to organize something which has a high entropy and go into slow entropy, you need to know what you are doing. And that actually is very important. And in some ways, this is relevant to the topic which actually I do want to talk about, which is speech processing. In speech processing, during a human communication, the person starts with a message. And the message, if you transcribe it in the sequences of sounds, has a bit rate less than 50 bits per second. But when it comes to speech here, you need more than 50 kilobits per second to transmit it reasonably well. And so you can do little mathematics here, which I put down on the slide, but I hope that I don't have to convince you about that. The speech comes into the ear of the hearing system of the receiver, of the listener, and listener can reconstruct the message which has a 50 bits per second. So the problem is very similar with the Maxwell demon. You need to know what you are doing in order to get to this feast. So you need the knowledge. So you need either little demon, which of course knows the magic, but let's assume that we don't believe in magic. So you may start putting knowledge which comes from expert beliefs and previous experience, or you can also get the measurements from the data. And this problem between the knowledge which is built in and knowledge which comes from the data is with us from the day number 1 of the speech recognition. So you can hardwire the knowledge, and then whatever you hardwire can be right, but it also can be wrong. So there are some problems. Wrong knowledge is not as good as no knowledge. Basically, once you hardwire the wrong knowledge, you are in trouble. You can get the knowledge from the data. Of course, data, you can say, do not lie. But for one, I mean, data is expensive. At the same time, you may start thinking, why am I relearning something which I know for sure? Maybe I don't need to do that. Maybe I should hardwire something. And then bad data is not as good as no data at all, because you can also use the bad data. So more knowledge you hardwire, the less training you will need. That makes some sense, right? So we still are struggling with this dilemma, knowledge built in or knowledge getting from the data. Suppose that we believe in some knowledge which should go into the system. When using the knowledge, the reasonable question is what kind of knowledge I should be using. For that, we need to look at the history of evolution of humankind and evolution of speech. So the whole story started 200 million years ago when animals got out of the water and got into the ground and had to learn how to hear, how to listen to sounds in the air. So that took quite a bit of evolution. It took about 200,000 years, and gradually, step by step, we ended up with Homo sapiens. Homo sapiens is pretty much the system very similar to what we have. Homo sapiens then started to think how to communicate, building on the knowledge, building on a hearing which was already present there. Hearing was there to prevent the animals and including Homo sapiens to avoid the dangers. So the sensory neurons got adapted to the environment. And you can trace it down, if you look at the speech, you can trace it down that properties of hearing do reflect the properties of the acoustic environment. Simoncelli and Olshausen has a very nice paper on this topic. Came Homo sapiens, another 200,000 years, when we had for evolution of speech, until we end up with a human being. This is a Roman Jakobson, and he reminds us we hear, we listen, we speak in order to hear. We speak in order for somebody to listen to you. So this is a quote, exact quote from his book. We speak in order to be heard, in order to be understood. So essentially, what I believe is that human speech evolved on the top of the human hearing. And what we hopefully will be seeing, that properties of hearing are reflected in speech itself. We will be using it to our advantage. So what is it that we want to do? We want to recognize speech. How? Well, we should be learning from human hearing, because the human hearing is optimal receiver for human speech. So we believe that we should be building properties of human hearing into speech. The reasonable question is why. You always have these three questions: what, how, and why. Typically, the why question is the most important one. Unless you can answer the question why, I mean, you better don't even get involved in the what and how. So why question is here, and has been asked for a long, long time. I've been working on speech recognition and in building the properties of human hearing into the system for quite some time. A typical question is, why would you do that? More data is always better than more thinking. This is I learned from Fred Jelinek, but he claims that he didn't say it. That was a Professor Eric Brill, who used to work at Hopkins, who was saying that. So essentially, this is something which engineers observed for a long time. If you want to improve something, you put in more data, right? And it became much more true with the evolution of the artificial neural networks. Those are nonlinear classifiers which started to be used sometimes towards the second half of the 20th century. Big advantage of the neural nets is that there is relatively little restriction on the form of the data which go in. That is one of the biggest advantages of neural nets. People I don't know to what extent you guys realize what kind of advantage it is. We remember when we were using Gaussian classifiers, always had to worry features had to be normally distributed and decorrelated and so on. Neural nets don't need that. And current advances of the neural nets actually allow for very new and revolutionary approaches to speech processing. Right now, we are in a stage where we believe that we can put the data in. It goes into the deep neural network with the big data, and information comes out, and we are done. I don't think that this is all that simple, as I showed here, but of course we see attempts like that definitely. Well, even more, these machines are better than human beings. According to some companies, basically, they are already claiming that we are beating the performance of human beings, but certainly the machines are very impressive. Here we have, of course, a machine which plays a game with the world champion, and you know that the world champion got beaten. So what do you do in this case? Either you give up, or you say, well, I might as well become a friends with the machines and try to think how they can help me. This is going to be a topic of my talk. So that was only by the way of introduction. What I'm after now, because I still want to survive a little bit in the field of speech recognition, what I'm after is this. You take the machine, which works very well, and you try to learn from the properties of the machine something about human hearing. Once you learn something about human hearing, you learn a relevant information which is needed for processing of speech. So it's not that it doesn't pick up just arbitrary properties of human hearing. Human hearing can do many things, among them decoding of speech. But if we are following this path, we hope that what comes out from the well-trained machine are the properties which are useful for recognizing speech. So once we learn about these useful properties, we can put it into hardware, or basically hardwire it into the system, and we get even a better machine. And the better machine is not only that it works better, but hopefully will also need less training data, because it can use all the knowledge which was extracted from the training data in the first place. And you can go, of course, in the circle. So it means that we have a good engineering, because we are engineers, but using the good engineering, we get a better science. We learn more about what the hearing system is doing, or what cognitive system is doing for recognizing speech. And then from better science, we get a better engineering. And the circle goes over and over. So let's start. Let's assume, I go back to the last century. Let's assume that we still don't know how to process the clean speech, the speech itself, raw speech. We start with the spectrum, and we will assume the linguistic message is represented by sequences of speech sounds. Again, we can discuss that to what extent this is true, but let's assume for a while this is what it is. So we have a labeled speech labeled by the sequences, by the labels which represent speech sounds. And we have a very large amount of speech data available, which is labeled. So you can get it hand labeled. Now we know how to do this automatic forced alignment transcription. We have a data, and we have a more and more and more data, because as we develop more machines, we use more speech data, we are getting more labeled speech data in principle. So in the middle of the last century, what we had was the technique which was called linear discriminant analysis. It's a linear technique, but it's actually surprisingly powerful. Advantage of the technique is that it is linear. That's why when you get the results, you can actually understand these results even better than the results which you get from nonlinear systems. LDA gives you a matrix of what is called discriminant vectors, and each of these vectors are telling you how you should project your original data in such a way that you preserve as much as possible of the discriminability. These vectors are ordered by eigenvalues, and so the vectors with high eigenvalues are more important than the vectors with lower eigenvalues. Discriminants, I already told you, are linear. That's why we can represent. So let's start. So we have a spectrogram, and we know which part of the spectrogram describes which speech sounds. So this is a sequence UI-yo-yo, and you know where the vectors come from. So you take the vector, and you say, well, it comes from the part of the speech which describes you. So I will put this spectral short spectrum, and I will label it with the label here. And I do it for all the speech which is available to me. So after a while, I have a box full of spectral vectors, and each vector is labeled with the sound from which it came. So the thing is pretty straightforward, and it's a simple thing to do if you have a MATLAB. Even if you don't have a MATLAB, I believe that you as a student can even write the LDA yourself. It just involves a couple of covariance matrices. After a while, after you do all that, you can look at the discriminants. And this is the first discriminant, second set, 4. You know how much discriminability each of these vectors carries. You can take the spectrum of the original spectrum, project it on the first few discriminants, and you can see you have a new system which will be which can describe the speech in terms of the projections of the short-term spectra on the discriminants, and you can evaluate it. You can evaluate how sensitive it is, say, to changes in the frequency. This has been done here. There was a little piece of the little Gaussian form which was moving either at the low frequencies or at the high frequencies. And what you can see that if you move it by constant amount at the low frequencies, effect is much larger than if you move it by the small amount at the higher frequencies. Very much what you would get if you were projecting your speech on the critical bands which are hardwired from the knowledge of human hearing. There's been a number of people who observed something very similar since 1994, Beam, Katagiri, Cohen, Kahn, Palival, Burgert, and Hermansky. So a number of people observed the same thing. What is interesting about it, this system had zero knowledge about human hearing. This system, all what it had was the speech, and speech was labeled with the labels which describe the phonetic quality of the particular instant of the signal. What you got out is the properties of human hearing. This is one of the basic properties of human hearing, which is like non-equal spectral resolution in frequency, known since the 30s of the 20th century by early masking experiments at Bell Laboratories by Harvey Fletcher, and since then repeated so many times that almost most doubtful people don't actually doubt this fact. Okay. Now let's move to 21st century. People, of course, try to get the same thing using deep neural nets, and you can. This is one technique which actually was done by Tara, where you take the waveform itself, this time you don't even bother to go into spectrum, and you design the projections of this segment of the signal on some basis functions. Then you have a maximum pooling and nonlinearity and the whole system of the NN-based ASR. But your question which you want to answer is what these projections are going to be describing. They are describing impulse responses of finite impulse response filters. So you can also look at the properties of these filters, which were designed as a part of the big DNN system, which on the first level had a weighting of the speech signal itself, segments of the speech signals itself. Again, number of people were doing these experiments. I know well about the experiments here, which were done at Hopkins. Here is one of the typical results. What you are getting is that each of the rows describes the impulse response of the filter, the frequency response of the filter, because once you have an impulse response, you can compute the frequency responses. These are the peaks of the filters, and you can see the peaks of the filters are pretty much following what you would get if you were trying to put in auditory-like filters. So linear projection, nonlinear projection, basically we are getting the same result, and the result is very much related to what human hearing does with respect to spectral resolution. What is the advantage of this auditory-like warping? Auditory-like warping makes a different speech of different human beings more similar. Here we have the spectrum of the male and the child, and you know, male spectrum looks very different than the children's spectrum, and these two things basically say the same. Let me check if the if the audio by any chance works. So you hear the message is the same, spectrum is very different. But after you do this projection of the auditory-like filters, suddenly you start seeing why is it that we are understanding the same thing, even when the color of the voice is different. Basically, this auditory-like spectral integration and smoothing makes these two spectra looking more similar. So it's obviously has advantage in speech recognition. Next step was that we start to be interested in temporal domain in general. We start playing with the things like how much I can recognize from the long segments of the spectral energies independently fed into the processing. So this is like a poor man's TDNN in some ways. We took 1 second of speech, went after some processing like cosine transform into the neural net, and then each of the neural nets would estimate the phonemes, probabilities of the phonemes at a given frequency. You fused everything into one neural net, and what you were getting out, vector of posterior probabilities of speech sounds, as comes to be useful for speech recognition. So we called it TRAPS, and it was done in 1998. And I'd like to point out that actually there were quite a number of very innovative concepts at the time in 1998. For one, we were using quite light segments, long segments of speech, 1 second. Then there was some hierarchical structure built here. So first level was recognizing or classifying sounds based on these individual frequency bands, and then we would be fusing the things by another net. So that was a kind of poor man's deep neural network at the time. What was interesting is that we were doing independent processing at different frequencies. And now this is something which we are, all these concepts we are finding now in many deep neural net recognizers, but that was in 1998. So we got interested in temporal processing, and we said, well, we have all these programs around, so we might as well use the same trick. This time we do the trick on the auditory-like spectrum because we already know for sure that auditory-like processing is good, so we start auditory-like spectrum, but we take a long segment at a given frequency, and again we label it with the labels, which is in the center of this long segment, because this long segment covers more than one phoneme. But this guy is called temporal vector yield, and you do it at different frequencies, and then so you get many vectors. Each of them is labeled with the phonetic quality which this vector describes. So we can use exactly the same processing which we did for the processing of spectral vectors, LDA, and ask ourselves what kind of projections should we be getting. So in this case, we are getting a discriminal matrix which will be describing impulse responses of finite impulse response filters. Here we have the first vector, here we have a second vector, third, fourth. These are the frequency responses. These frequency responses indicate what is it that you want to do here is to enhance the components. This time you work in something which is called modulation frequency. So modulation frequency components between 0 Hertz and about 10, 12 Hertz. You should suppress anything which is less than 1 Hertz, which is changing much slower. And you should also suppress things which are faster than 10, 15 Hertz. That's what is being suggested by this linear discriminant analysis. Again, first experiments were 1997, but we repeated it again under some DARPA funding in the 21st century. Still the same answer. Interesting thing is that we are getting very similar filters at all frequencies. So it's not like that high frequencies like the high of rates of change, lower frequencies, slower rate of change. Pretty much every filter says you better keep the changes between 1 and 10 Hertz. What is interesting about that? Again, it has been known since 1928 that human hearing is most sensitive in the range between 1 and 10 hertz. Those were very early experiments from the laboratories. This is a frequency response of the first discriminant. This is well, upside down, because here we have a sensitivity, here we have a gains, but it tells us the same thing. Here I'm just showing something which we didn't talk much about, but you can actually look at the frequency responses or responses of your cortical neurons. I think that Nima Mesgarani was talking about spectral temporal receptive fields in auditory cortex a little bit more. So you can take a number of these cortical neurons and you can be asking yourself, what is the dominant temporal properties of these cortical neurons? And isn't there some similarity? Yes, there is, because they also like the frequencies between 1 and 10 hertz. Your brain likes it. Your hearing likes it. This is a physiology, psychophysics. This is an engineering. We can now look a little bit also into speech. The speech actually, if you look at a lot of speech, independent of type of material, sentences, conversations, interviews, audiobooks, they always, you see the maximum energy in this range between 1 and 10 hertz. For different languages, we have American English, Mandarin Chinese, French. Again, I mean, the peak is always around 4 hertz. It's somewhere around around syllabic rate. But it's totally amazing how similar, if you look at a lot of data, there's, I think, audiobooks and a lot of data measuring the dominant rate of change. And so now you see why the LDA filters like to enhance something which is a dominant in a speech, because probably people learn how to speak in order to be heard well, in order to hit the maximum sensitivity to modulations, which we know from human hearing. And it's been built in by the physiology of the processing chain. Why is that good in engineering? It is good in engineering because if you suppress the low modulation frequencies and high modulation frequencies and keep the modulation frequencies which are dominant for transmission of the speech, you may be able to get rid of some very unpleasant things. Here we have an example where we had a speech.
Beat.
And speech was filtered. By filter, which makes the vowel here with a totally flat spectrum. But still, you of course understand what people are saying, right? Because the
Beat.
Sounds like a filtered speech, but since the filter was fixed in time, the rate of change was the same. And if you do this processing, where you are enhancing the modulation frequencies which carry the speech, suddenly you start getting the very similar results. Unlike the spectrum. What is good about it? If you are an engineer also, you should look and if it helps you in some situations. So this was the situation where there was a recognizer was trained on one set of data from Belcore at the time. It was when it was tested on a Belcore data, you were getting very respectable error rate. When you tested it on different data in a lab which was in Colorado, suddenly the whole thing broke. However, after doing this processing, suddenly you were getting very similar results, because what happened was that, of course, difference between two recording environments in New Jersey and Colorado was such that the low frequencies basically were very different. Right? The DC was very different. After filtering, it became very similar, and the recognizer, of course, was working very well. Well, of course, it's tempting to do the same thing with a neural net. So neural net one looks like this. I mean, you have an input, and input represents the time frequency point in a spectrogram. If you put in the whole vector of the time frequency of the spectral values, what you get out after you train the whole thing, what you get out, again, are going to be linear filters, which you can interpret as filters on the modulation frequency filters. So here are the filters, and here are the frequency responses of the filters. And this is a range between 1 and 10 hertz, 1 and 10 hertz, so 1 and 10 hertz. And you can see you are doing basically qualitatively very similar result. So linear processing, nonlinear processing, always you are getting the similar answer, which is you better remove the slowly changing and fast changing components and keep the components which, modulation frequency components which carry the speech. So the conclusion here is, if you want to classify the speech, then you should be using relatively long segments of the speech, at least the syllable length, because you want to be able to see this dominant change, the modulation frequency which carries the speech. Important information about message is in the time frequency patterns about the syllable length long. You can double check on that using mutual information. You can actually ask yourself, since you have the label data and you have the spectrum, you can ask yourself, if I look at the different parts of the spectrogram, how much information these different points are telling me about the underlying structure of the speech sounds. Here is the answer. Pretty much information is at all frequencies. This is a frequency response. This is in time. In time, information is spread over about 200 milliseconds. Here we see it in the two dimensions. So we are now quite certain that these are the points which actually we should be looking more closely in. So we can look at the different, again, LDA technique, but this time we are not going to use the temporal vectors and spectral vectors, but we are using time frequency patterns. And what we will get out, so we will take this time frequency pattern and we will label it with a phoneme which is in the center of this pattern and feed it again into the linear discriminant analysis. And what comes out is this. You get the two-dimensional filters this time. But what is interesting about these filters, that different filters are enhancing different frequencies. Some of them, of course, are covering most of the frequencies, but some of them go for low frequencies, some of them go for high frequencies. So something is interesting here. So the processing of these two-dimensional patterns, when you allow yourself to also enhance different carrier frequencies, such as that you should be making projections where part of the speech is used. I mean, some of the projections are enhancing low frequency, some of them high frequencies, some of them mid frequencies. Hey, I mean, since we are working with the neural nets, we might as well do the same thing with the neural nets. So instead of feeding in individual points, we are feeding in as an input the whole time frequency patterns. So what comes out? We will get projections very similar from LDA, but this time we are using the whole machinery of the deep neural network. So what we do is that we take the input and we project it on different time frequency patterns. Then it goes into the whole deep net, and we are trying to classify the phonemes at the output. How does the result look? Again, very similar. I mean, the qualitatively similar. Like different projections are enhancing different frequency ranges. Low frequencies, high frequencies, where are they? Mid frequencies, high frequencies, and also the different rates of modulation in the time and in frequency. So essentially, this technique is telling us what you should do is that you take the reasonably long segment of the signal. We started, I think, with 500 milliseconds, half second here, and you should project it in such a way on two-dimensional filters so that the different carrier frequencies and different modulation frequencies are being enhanced in each of the stream. So essentially, you can see it a little bit like this. You start with the original spectrum, you have these projections, and each of these projections actually represent one way how you can describe this original spectrum. So this is one way how you can look, one filter, a particular filter which you look at the spectrum through this filter. Here we have how it looks when you look through this filter. You get here 32 different ways of looking at the signal. And these 32 different ways to looking at the signal are fed into the input first hidden layer of the neural network to classify speech sounds. That would make very happy some people from the last century from the laboratories, namely the people who were working on concept what is called articulatory bands. Articulatory bands are results of the very, very large amount of perceptual experiments where people tried to cut off certain frequency ranges from speech and try to follow what's happening with intelligibility. Essentially, the conclusion was that you can divide the whole speech into a number of frequency bands, and each frequency band carries equal amount of intelligibility of the speech. And then after you combine these frequency bands, then your intelligibility, of course, goes up. But what is very interesting, that if you take about 50% of the spectrum, you are still getting a very reasonable rate of recognition, about 70% recognition of correct, of nonsense syllabi, which can translate into almost perfect recognition of continuous speech. So here it is. We start with the spectrogram, and you can cut off center frequency. You get 70% accuracy in recognition of phonemes. But you can also keep exactly the one which you cut out and cut out what you had before, and you again get a 70%. And if you cut every second one, again, you get a 70% recognition accuracy of the syllabi, enough to recognize speech. So essentially, what these experiments are telling you, you don't need the whole spectrum at all. Basically, all you need is enough of the spectrum of the speech to recognize the speech. And this is very interesting from an engineering point of view, as we will see a little bit later. At this point, we have to go to hearing for me to convince you that this is exciting. Hearing looks like this. You start with the speech signal, and you go through a number of stages, and you get into the brain or the auditory cortex. On the input, you have a sampling of the signal. You have spikes about every 1 millisecond, about 1 kilohertz sampling rate. On the level of cortex, the sampling rate is about 2 orders of magnitude less. Cortex is essentially looking at the big things. Input is looking at the signal, but cortex is looking more like at the phonemes or syllabi. But what is also interesting is if you look at the number of neurons which are available to you. At the periphery, you have maybe about 100,000 neurons. But in the cortex, you have 100 million neurons. Out of that is maybe about 10 million active for any given task. So it means that what you are doing is that you are slowing down the recognition rate. You are interested more and more in the larger segments, but this number is telling us that you are providing for many, many more ways of looking at the signal. So that's why all these experiments with the multiple filters and two-dimensional filters are interesting. Another property of human hearing is that at the periphery, what you get is that you analyze the signal into different frequency bands, critical bands, right? And so basically spectral analysis happens at the periphery in the cochlea. But all the way to the auditory cortex, whatever the cochlea does, the dividing signal into different frequency bands is being preserved all the way to the cortex in a tonotopy. Means that low frequencies are tickling one part of the spectrum, a different part of the cortex than high frequencies. So why is that? It seems like that what human hearing, or in general mammalian hearing in general, or actually even some bird or reptile hearing, which has a spectral analysis, found it very useful to subdivide the acoustic signal into the individual frequency band and then process each of these bands independently. You can see that, I don't know to what extent Nima was mentioning it last week, but here we see 2 different cortical neurons, and you see that each of the cortical neurons appears to be doing something else. So the responses are relatively long. This is a quarter of the second, can be relatively long. Some of them are short, some of them are long. but they are also paying different attention to different parts of the spectrum. This one is for high frequencies, this one is for the low frequencies, this one pretty much does the differentiation of the whole spectrum. Typical receptive field looks like this. It's relatively long and it's relatively narrow. So maybe frequency selective up to about 2 octaves and a long time for about 200 milliseconds. So we have this hearing. Now, how do we speak in that case? We have a speaking system. We have the system which has been designed for something else, for breathing and for eating, but we learn how to use it for generating speech. If you use the vocal tract for generating speech, anytime you change the shape of the vocal tract by lifting up the tongue or closing the lips, all frequencies of the spectrum are being changed. This is maybe I go a little bit fast here, but this is what happens to your resonant frequencies if you are moving tongue constrictions along the length of the vocal tract. And you can see that every single resonance is changing anytime you move the position of the vocal constriction. Anytime you close it, also the whole spectrum is changing. So from motor control, it goes into the critical elements of the speech production. It changes the whole shape of the vocal tract, but all changes in the vocal tract are being reflected at all frequencies. This is a big advantage because then, I can only use the half of the spectrum and still get enough information about the shape of the vocal tract, which in turn describes what is being said. Another thing with the speech is that it moves relatively slow. Here we have the vocal tract in production of speech, and you see that its changes are not terribly fast, right? Because the vocal organs have certain inertia, the whole control system has a certain inertia. So if people want to produce the sequences of speech sounds, instead of coming out the sequences, what comes out are the co-articulated sounds. So the whole thing basically gets smoothed in time. So after all, if you look at it, we have the vocal tract, and we have a hearing system. So every change of the tract shows at all frequencies of the spectrum. And the tract shapes are not happening very fast, but hearing is frequency selective, meaning that I can pick up information from different bands of the spectrum, and it's relatively sluggish. That's what we have seen when we're doing analysis of the cortical receptive fields. So means that the hearing is quite happily capable of doing following things. You start with this information, 50 bits per second, but it goes into the coding, it goes into your speech production organs, and that introduces redundancies in frequency and in time. So what comes out is a speech signal with the redundancies built in. So that's why you already are getting much higher information rate. Comes the noise, but the message is being protected by the redundancies which you built in the speech production. And then it goes into the decoding. Decoding is, of course, your hearing system. But the redundancies which you built in actually are already using the fact that hearing can deal with these redundancies and in some ways strip them off, get the information out, information about the message. And that's why you get a 50 bits per second message. So in frequency, tract acoustic distributes the information at all frequencies of the speech spectrum, but perception, hearing selectivity allows for decoding of the information independently, different frequency bands. You build the redundancy in time by co-articulating, basically. So this is in production. And in perception, this temporal sluggishness is being compensated by the ability of human hearing to process relatively long segments of speech. And so pretty much the system is quite amazingly amazing. This is a slide which probably is a little bit busy for this late time of the talk, but we are now trying to pursue this whole concept of the human-speech communication in this way. So you start with the sequences of speech sounds which you want to transmit. It goes into movements of the vocal tract. Because of sluggishness, you get a co-articulated information where information about each segment is basically spread in time and overlapping. Then it also gets spread at the same time in a frequency, so you get the very similar pictures in terms of the information at different frequency bands. So speech signal comes here. Corruptive speech signal, basically signal may get corrupted in a way to perception. You form the spectral streams. That's what your selectivity of human hearing comes. You get the different pictures at different frequencies. They are not perfect, but you get a number of them. So if you put this through the filters, you get information about these segments here in a time corrupted. But by fusing it in a smart way, you may be able to get out the original segment. If you want to know more about it, the paper just came out in speech communication. Why is that good for engineering? We can build a system which basically works a little bit like a human hearing, because we are dealing with human speech and we can't kind of believe that we know how the information is coded through the human speech production. So we start with the signal. We take a reasonably long segments of the signal, at least a syllable, a little bit more is probably better, and we form the different streams, different frequency streams. And then when we are fusing these streams, we have a performance monitoring module, which helps us to pick up the appropriate combination of the streams in order to get a reasonable string of speech sounds and sequences of words. Crucial element of this scheme, which we are very much struggling with, is this performance monitoring module. Because performance monitoring module needs to be able to tell how good the result of the appropriate choice of the frequency of the individual streams is without knowing what people are saying. Because, of course, what people are saying is the information. But what you are going to use here in performance monitoring is more this redundancy, which is built into the system. So you want to use something which is independent or relatively independent of the message. So here, am I doing fine? Here maybe I spend a little bit of time on performance monitoring because this is a problem which is dear to my heart. Here we have two different posteriograms carrying the same message, except that this one is corrupted. You can tell, right? I mean, if you are looking at enough posteriograms, that's what you know. So one of the techniques is using a difference, that you measure the difference between a posterior vector at given time and posterior vector at some distance in a time. And if the data is clean, this distance in average is large because these segments are in average, sufficiently different. But if the signal is noisy, your difference is basically becoming diminishes. So this is what we call M measure, and it can be used for guessing how good output of your neural net is without independently of what people are saying. Another technique, which actually initiated when Imam Esgarani was in our lab as a postdoc, was you ask yourself, so I don't know what people are saying, but in average, the output should be somehow similar. I have a training data, and I know my classifier is working as well as possible on its training data, so I have some gold standard, and I will be trying to look so I build a model on the output from the classifier on its training data, and then I will see how well the data on the test, which can be corrupted, are fitting the model. So one of the techniques which we are using quite a bit is that we train autoencoder on the output from the classifier on the training data. And so first we train the probability estimator, but then we train this autoencoder here, which tries to replicate the output from the classifier on its output of the classifier, which forms the input to the autoencoder on its output. And when the test data come, you just measure the difference between the KL divergence between the posteriors, the input of the autoencoder and output of the autoencoder. If the KL divergence is large, you know that your output may be different than what you trained your your performance monitor on. Here is one system, just to give at least some numbers in this talk, because I know I didn't give many, which just came out in a PhD thesis at Hopkins, by Harish Malidi. So he had this system here. He formed different frequency streams. I think he used the 7 streams. And then he trained the fusion by the technique which is now becoming quite popular, which is like drop out different frequency bands. I know that the paper just came out from Google, so finally the community is getting some attention to this technique. Harish was doing it for even earlier, because give him a credit. I mean, he deserves some credit for that. But then at the output, you look at the performance monitor and you try to form a better combination of streams. So here we see something which if you do nothing, you get a 12%, 12.5%. If you just do the individual spectral streams, you do better, you get about 11%. If you train with the stream dropping, there is quite a bit of improvement. And if you put on top of that performance monitor, you get another performance boost. And if you knew how to form the best combination of streams, that would be oracle selections. So difference between 9.6 and 7.9 is still something which we have to fight for. Instead of conclusion, I would like to somehow summarize what I try to convince you about to the best of my abilities, which may not be the perfect. I believe that human hearing evolved to fit, human speech evolved to fit the properties of human hearing. That's why if we optimize the speech technology on speech signal, and we design the speech technology in such a way that we can actually look at some of the properties, what is it that we design, we may start seeing relevant properties of human hearing, properties which are relevant for decoding of speech. This is Fred Jelinek's workshop. So I took the liberty to prepare this one slide. And this has been reported in New York Times when Fred passed away in the obituary. He said, oh yeah, Fred was always saying airplanes do not flap wings. Why would we put in properties of human speech communication chain into speech recognizers? I just want to say this is not what Fred was saying. This is exactly what Fred was saying in writing. He wrote it in one of the little letters to editor. Airplanes do not flap wings, but they do have wings nevertheless. So it means that there are some properties which we observe in nature which actually can be useful and which are used. Of course, we should incorporate all the knowledge which is reliable, which we have of hearing, speech production into our system. But first, we have to figure out how to parameterize it so that it can fit into the system, and how to estimate the parameters from the data. And I took the liberty to put it in bold. There is no other way. And I think that we are succeeding there, at least to some extent. Well, we are succeeding in trying to do what Fred was suggesting. And on this note, I think I would finish so that we have a little bit of time for discussion.
Thanks, HYNEK, for this inspiring, very interesting, great talk that I think has inspired also many questions. So, are there questions? Yeah.
Since most of evolution was, most of the evolution time was spent in developing hearing for surviving, do you think that we should train machines with sounds that are related to survival, like natural sounds of mammoths coming at you and things like that?
Well, it depends what kind of system you want to design, right? I mean, if you want to design a system for speech, my point almost was not necessarily, because hearing can do many, many things. Not everything is being useful for speech. And that was a long time a problem of auditory models. People know a lot about hearing. They would build a model of hearing, and then they would think if they put this model of hearing into speech recognizer, they will get a good result. And not necessarily, because this model of hearing can be enhancing something which is not necessarily important for speech. So not everything is being used for decoding of speech. I don't know, did I answer that?
Yeah.
Other questions? I have one. We've seen that with information coming from modulation, frequency modulation spectrum, and what is exploited at this level by the hearing system, there is an enhanced communication between humans. Today, in these days, we are particularly exposed with problems related to reverberation, noise, and in particular, unstationary noise. This is very hard to manage more than the stationary one. So I was wondering if you have some direction about how all the knowledge that can be captured with the neural network, deep neural networks at this level could be exploited, for instance, to make system more immune to non-stationary noise.
So let me start with the easier part, which is like, or more difficult part, which is like when your disturbance have a similar rate of change as a speech. I can be competing speaker, or can happen to be whatever motor vehicle which actually has a 4 hertz rhythm. Then I wouldn't look at the modulation frequency necessarily to help us. But in many, many noises, like noise, very often the noises are more stationary, that you can, if you filter out everything what is slower than about 1-2 hertz, you probably will be getting some advantage. Or noises are very impulsive. If you filter out, if you smooth out the modulation spectrum so that you don't keep the rates of change higher than 10-15 hertz, you may get rid of a lot of these impulsive noises. So the good thing to remember, speech is between 1 and 15 hertz. Subsequently, sampling of the features should be about 25-30 hertz, not 100 hertz. That's what we are learning gradually. But also, there is no point keeping things slower than 1 hertz. Of course, we all do the spectral subtraction, meaning that we are filtering out DC or very, very low modulations. But you can safely go to 1 or even 2 hertz in order to keep enough of the information about modulations. When it comes to reverberations, it's also very interesting. Reverberation, if you look in modulation spectral domain, reverberation functions as a low-pass filter on modulation spectrum. So there will be differences in the changes which are faster maybe than 5-6 hertz. I think that it's always good to keep as much as possible around this syllabic rate about 4 hertz. But smoothing out the changes which are faster than 4-5 hertz may give you some advantage in reverberations. And we can discuss a little bit more because that's something which we are currently interested in. My modulation domain is actually not bad to deal with reverberations.
So
thanks.
I have a question from Sanjeev. He texted me, so I'm going to say it. But actually, I have a follow-up after that. So a question for HYNEK on articulated band experiment from the 1950s. So by using dropout in the early layers of, say, a standard TDNN with the log spectrum input, are we replacing human hearing? Let me finish. Is there a way to test it, example, by computer error made by human on the original Fletcher data and with the error made by the DNN classifier? not shoot overall error like Hershey experiment, but actually speech example for the 1950 on which human machine makes errors?
So as far as the human perception is concerned, unfortunately, nobody repeated these experiments. They were done since 1926 until 1949. They were very expensive, and those were the days when companies still believed that understanding human hearing can be useful for development of the technology. Subsequently, we ended up with a Bell system. Nowadays, companies, hopefully, if they get interested in this part of the problem, they would have to put down a little bit of money to run the perceptual experiments, because perceptual experiments are expensive, but a lot of data is available. People criticize it very often because they say, oh, those were nonsense syllabi, and how relevant it is to speech. I'm convinced that it's quite relevant to human speech as long as you bear in mind what you are looking at. So looking at the answer, Sanjeev, where is Sanjeev over there? There is Sanjeev. Answer the Sanjeev is that there's a lot of human data which is available, which may be very much worthwhile looking at again. It would be very good if somebody is willing to run the perceptual experiment. Experiments are relatively simple. What you are doing is that you are high-pass filtering speech, low-pass filtering speech, corrupting the high-pass filtered speech, corrupting the low-pass filtered speech. Nowadays, we can probably even do a decent way of bandpassing the speech. You have to realize when Bell Laboratories were running the experiments, they didn't know how to build a decent bandpass filters. They knew how to build a good low-pass filters and high-pass filters, and based on that, they came up with this concept of articulatory bands, and I would be happy to give 3-hour talk on these experiments. They were very interesting.
But you cannot use...
But answer is, as far as the human data, quite a lot is available. And we
cannot use it in the original data, like the fracture data?
They don't exist because they didn't have recordings at the time. So they had a crew which was producing the speech. We replicated some of this data with Mark Lieberman. It's called Fletcher data. Okay. And so some data were produced which maybe, but they were not filtered. It's just like this nonsense syllabi as reported by Bell Laboratories. It's available, not much work was done with that. Okay.
So I have more questions. So in your work for the multi-stream, okay, so are you telling us that the speech is more complex, that you have to take it by piece rather than take it globally? Or, or the actual systems that we have, the models we have are not power enough to handle it completely by the whole spectrum versus piece by piece?
If you use all information in the signal and speech is clean, you are the best, in best shape. All this concept of articulatory bands and the way we are thinking about it in terms of the multi-band recognition aims at more robustness in presence of frequency localized noises. So if you leave something out, you will lose a little bit, but you will not lose as much as you think. You can do quite well. I mean, Sanjeev was actually asking about this dropout band experiment. Dropout band experiment is telling you, or the systems which people are now using, is that you don't actually need all the time all the frequencies. And that's what articulatory bands are telling you, right? You can drop out half of the spectrum and still get a decent recognition rate. So, but you will never get better than using everything. But you do get better if you drop out the part of the spectrum which is corrupted. Yeah.
First of all, Sanjeev said thank you, because I'm getting in my watch. The second question is, so now lately people are using wave as input to DNNs and all other features. Is the brain doing, because DNN is supposed to do the same thing, is the brain doing feature extraction as well?
Oh my God, say it again.
So no,
brain and deepness is a tricky.
Yeah, people are using a waveform as input to the directly. So they learn the feature automatically. Mm-hmm. Is the brain doing the same thing? Is it learning features?
Well, the brain is working in a number of stages. And maybe we can bring up
because the hearing system is supposed to one to give the feature information to the brain, right? So it is. I'm not sure.
Brain is using output from the periphery. Periphery does the spectral analysis. I mean, it's good that people show repeatedly that whenever they start with the waveform, they get a spectral analysis which is similar to cochlear analysis in the periphery of the human hearing. I personally say don't bother with that even. I mean, we know enough about the periphery that we don't have to prove it over and over and over again, though it's a good topic for students, right? But I think what we know much less about the higher levels, what happens after the auditory nerve. Auditory nerve is the one which goes from the ear into higher levels. That's where we are learning, and that's where the receptive fields come from, two-dimensional filters. And
Sounds good. Any more questions?
No,
So, with all your experience in the field on speech, do you think that DNNs will replace the signal processing?
well, I mean, so in some ways, I'm a DNN do spectral processing, but I try to make point that some of the spectral processing does make sense from what we already know human hearing is doing, so I might as well hardwire the periphery, for instance. And the little bit danger with using relying entirely on DNNs is that you keep learning over and over again the same thing which we already know quite well about the human hearing. Namely, human hearing does the spectral analysis. So I wouldn't be replacing it, but I would say thank you very much. I already learned I should do critical belt-like spectral analysis. I will do it, and maybe I will let in general, classifiers should be doing things which we don't know about yet. For this, you need to use the data, and you like to ask the classifier, what is the best way to process it, because I don't know how. Once you get the classifier, and if it is structured in the right way, it would be great to be able to look at this classifier and say, oh, I see this is what this classifier is doing. And it can be sometimes simple classifier like LDA. So LDA is easy to look at, but once I know what I should be doing, I should just say, okay, I know, I don't have to learn it anymore. I will learn a little bit more. So replacing, I don't think so. Yeah, I mean, I should have said it at the very beginning, but it was a long answer because I was answering as I was thinking, right? But this, I truly believe, is we shouldn't be always learning from the waveform, because it's the same thing like this starting to build a human being from the animal which was 200 million years ago, because you already know there is a structure. And the structure is there because it was useful for listening to important things. And the structure is being used for designing a human speech. So structure we should be somehow aware of. And so answer is no.
Yes.
So, you heard Nima's talk, right? You watched it. Nima's talk.
Nima talk,
Yeah. Okay, so he said something that I'm not sure if I understood fully, but he said that there are like parts of the brain that like one particular speaker, or very particular speakers they like, or they get excited when those people are talking, or with similar properties. So I wonder if the whole technology, the speech technology, when we try to insert speaker adaptive training fairly soon into the process of the training, if it's correct thing to do, maybe we should train like speaker dependent models for, let's say, units of speakers, tens of speakers, and then somehow combine on the top of it.
It would be interesting if we knew how to cluster this large number of speakers which we have to deal with, like infinite, right, into reasonable number of clusters, like 2 males and females, and we do that. As you know, speech recognizers do exist, which switch between male and female. So if you make a reasonable number of clusters, you can see it as a processing streams. And then you only have to design a technique how to pick up the good stream or good combination of streams. And maybe that's also a struggle which we have with all this performance monitoring, because performance monitoring has applications beyond what I was showing. So in that case, it may help you. And it wouldn't be a bad way of going. It wouldn't be a bad way. But human hearing, I think that's what Nima was also saying, is capable of focusing on a particular speaker, means that they must have some representation of one speaker and one representation of another speaker, but it's also quite capable of ignoring these differences. That's the little bit of problem with cognitive systems in general. They are quite flexible, and you get what is it that you need. The human speech processing system is, I think, exclusively specialized for receiving the messages. But if you need to recognize speakers, you can to some extent do it. Especially if the differences are large, or speakers are well known. But I think that primarily what the whole system is designed for is to recognizing messages independent of the speaker, independent of the noise. But a good question.
Yes, it's. You have a very in-depth analysis here, of course, of all, let's say, English, and I even saw Chinese mentioned. And we know exactly how the phonemes are being vocalized and the frequency bands that are relevant. However, the human speech system allows so many other more exotic forms of communications. I'm thinking about other languages, click languages. We could communicate via singing and whistling if we wanted to. So my question is, should we study more, of these exotic languages? I mean, are we missing anything fundamental by looking too much into, let's say, Wall Street Journal?
To some extent, yes. I mean, you probably know the experiments where you deal with the children. They can do many distinctions, which they are being born with. And then essentially, as they are learning how to process the target speech, mother tongue, they are forgetting about the distinctions. So essentially, rather than learning a new distinctions, you are forgetting how to make a distinction between R and R in Japanese, for instance. Japanese children can do it quite well, but the Japanese, all the children already lost the chance. So certainly, I mean, I would say it's good to study the other languages. Of course, economy of the enterprise tells us let's deal with the English and Mandarin Chinese, but at the same time, I mean, of course, it's being done. And maybe we can learn something new, though. In terms of modulations, the picture which I was showing, the experiments from Maryland, the modulation spectra in average are amazingly similar for a number of languages, in average. It doesn't tell you about the details, of course, this average over. So basically, deep in my heart, I believe we are all the same. But we, of course, evolved in different ways. I mean, I cannot speak good English because I was born Czech. So
I have one last question. The last slide you said that the speech production adapted to the human hearing.
yes,
Okay.
yes.
So if we want to create an automatic system that simulates the human brain and hearing system, it means that we need to know the limitation of the artificial system. So the speech system, we should change our way to talk to the machine versus the way to talk to human.
Oh, that's a tricky part, right? I mean, but of course, I mean, people do learn a little bit how to communicate with the machines which are useful, right? We all learn how to drive the car, even when we're born by driving a car. So if there is a lot of speech technology which is working in a particular way, I would believe that people will adapt to that to some extent. Doesn't mean that they have to adapt necessarily for communication among each other, but they might. The teenagers already talk differently because they use SMS.
Yes.
right?
they're right. Yeah,
Or
informal
truck
language.
drivers have the whole code of, yeah, it's possible. I mean, but I only hope that we will still talk to each other and not only to machines. So.
All right. All right. I think we can.
Okay, I think there is a question there.
Oh,
Maybe this question sounds superficial, but I always ask myself why there's words like I means me and I like I, and these are had the same pronunciation although different meanings. Is it because limitation of of human being pronounced it, or some other reason?
I have no idea.
Thank you.
Thank you. It's a good question, but honestly, I don't know.
All right.
So thank you again to HYNEK, and let's do an applause.
Thank you.